Hello, friend. Welcome to another quiet journey through the cosmos. Some nights the sky feels closer than it should. Stars hum in frequencies we can't quite hear. And somewhere 140 million miles away, a red world spins in silence, holding secrets older than memory itself. Tonight we're drifting toward Mars, not the Mars of science fiction or conquest, but the Mars that whispers through data streams and dust-covered sensors. The Mars that China's Zhurong rover touched, listened to, and quietly began to understand. What did it find there in that ancient stillness? What stories does red dust tell when you lean close enough to hear? Before we begin this gentle drift across space and time, if you find comfort in these quiet journeys, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. These small gestures help others discover this place of rest and wonder. Now, let's drift. The year was 2021. On May 15th, as Earth turned through another ordinary spring day, something extraordinary was happening in the darkness of space. A spacecraft called Tianwen-1, its name meaning questions to heaven, released a small lander carrying an even smaller rover. Together, they fell toward Mars drawn by gravity's ancient pull, crossing the threshold between orbit and atmosphere at nearly 12,000 miles per hour. 7 minutes of fire. 7 minutes where heat shields glowed white-hot and parachutes bloomed like flowers in a thin, cold wind. Scientists call this the 7 minutes of terror. Though terror seems too loud a word for something so precise, so calculated. Perhaps it's better described as 7 minutes of held breath. 7 minutes where years of work, billions of calculations, and the dreams of thousands of people condensed into a single burning question. Will it survive? It did. Zhurong, named after an ancient Chinese god of fire, touched down in a place called Utopia Planitia. Utopia. The word itself carries such weight, such irony. A perfect place named by astronomers centuries ago, who saw only shadows and light through primitive telescopes, who imagined oceans and civilizations on that distant red dot. But here's what they couldn't have known, what no telescope could reveal. Utopia Planitia wasn't named wrongly, not exactly. Because beneath Zhurong's wheels, beneath layers of rust-colored dust and ancient stone instruments began detecting something remarkable, something that whispered of a time when this place truly might have deserved its name: water, or rather, the memory of water. Scientists estimate that 3.5 billion years ago, perhaps as recently as 9 billion years ago, Utopia Planitia sat at the bottom of an ocean. Not a small sea, not a lake, but an ocean that may have covered nearly a third of the planet's northern hemisphere. Imagine that for a moment. An ocean on Mars lapping against shores that no longer exist under skies that once held clouds thick enough to rain. The evidence comes quietly, methodically. Zhurong carries a ground-penetrating radar system, a tool that sends pulses of electromagnetic energy deep into the soil and listens for echoes. Different materials reflect these pulses differently. Rock sounds one way, sand another, and sediment the kind laid down slowly over millions of years. By flowing water has its own distinct signature. The radar revealed layers, 16 distinct layers in some locations, each one representing a different epoch, a different chapter in Mars's long story. The deepest layers, buried beneath 80 meters of younger material, showed patterns consistent with sedimentary deposition, patterns that on Earth would unambiguously indicate the presence of ancient water. But Zhurong's instruments went further. They analyzed the composition of rocks and soil, measuring the presence of hydrated minerals, substances that form only in the presence of liquid water. They found aqueous mineral silicates that had been chemically altered by water over long periods of time. Not flash floods or brief wet periods, but sustained stable water that persisted long enough to fundamentally change the chemistry of stone. This wasn't China's first hint at Martian water, of course. NASA's rovers Spirit and Opportunity had found similar evidence years earlier in different locations. Curiosity, still exploring Gale Crater, had discovered ancient stream beds and minerals that could only form in neutral pH water. Water that wasn't too acidic, wasn't too alkaline. Water that, in theory, could have supported life. But Zhurong's findings added a new dimension to our understanding. While American rovers had focused on equatorial and mid-latitude regions, Zhurong was exploring the northern plains, the flattest, smoothest terrain on Mars, the place where an ocean, if it existed, would have been deepest. And here's what makes the heart pause. If there was an ocean here, it wasn't brief. The sediment layers suggest it persisted for hundreds of millions of years, long enough for chemistry to become complex, long enough perhaps for the first uncertain steps toward biology to occur if conditions were right. Think about Earth for a moment. Our oceans appeared roughly 3.8 billion years ago. Within a few 100 million years, perhaps as quickly as 3.5 billion years ago, the first single-celled organisms emerged. Life didn't wait. It couldn't wait. As soon as conditions allowed, chemistry began its patient exploration of all the things it might become. Mars had water at the same time, the same chemistry, the same basic ingredients: carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, all present, all available. So, what happened? Why does Earth shimmer with forests and oceans and the endless conversation of living things, while Mars spins in silence its ancient seas long since vanished? The answer isn't simple, and it isn't quick. This is where our story deepens, where the questions multiply, like stars emerging as twilight fades. But before we can understand why Mars lost its oceans, we need to understand something more fundamental. We need to understand what protects a world, what keeps an atmosphere close, what allows water to remain liquid rather than boiling away into space or freezing into permanent ice. Scientists sometimes describe Mars as a planetary fossil, a world that stopped evolving billions of years ago, preserved in a state that offers clues about what all rocky planets, including Earth, experienced in their youth. But fossils can be misleading. They show us what was, but they don't always reveal the transition, the slow or sudden change between then and now. Zhurong's mission was designed for 3 months, just 90 Martian days, or sols as scientists call them, to explore, to gather data, to send back whispers of discovery, before dust covered its solar panels or cold damaged its instruments beyond repair. But it exceeded expectations, as these quiet mechanical explorers often do, operating for more than a full Martian year before entering hibernation mode. In that time, it traveled nearly 2 kilometers a distance that sounds small until you remember that every meter was new territory, every stone a potential revelation. It worked through dust storms that blocked out the sun for weeks. It endured nighttime temperatures that plunged to minus 130 degrees Fahrenheit, cold enough to freeze carbon dioxide out of the air. And it found again and again evidence of water's patient work, not just in the deep layers revealed by radar, but in the shape of rocks themselves, erosion patterns that suggested flowing liquid, chemical weathering that indicated prolonged exposure to moisture, small features that scientists call ventifacts, stones carved by wind, but wind-carrying particles of ice, creating textures that tell of an atmosphere, once thick enough, wet enough to blur the line between air and ocean. The Chinese National Space Administration released these findings slowly, carefully, each paper peer-reviewed and scrutinized by international scientists. This is how science works at its best, not through proclamation, but through patient accumulation of evidence, each fact-checked and rechecked, each conclusion tested against alternative explanations. And here's what emerged from that careful process. Utopia. Planitia wasn't just an ocean bed. It was a place where water persisted long enough to create a complex hydrological system. There were likely shorelines, river deltas, where fresh water from higher elevations mixed with the standing ocean. There may have been tides driven by Mars' two small moons, Phobos and Deimos, which pulled at the water just as our moon pulls at Earth's seas. Can you picture it? Not the Mars we know, cold and rust-red and silent, but a younger Mars, a Mars of movement and change. Waves lapping against ancient shores, clouds gathering and dispersing, rain perhaps falling on stone that had never before felt water's touch. It lasted hundreds of millions of years, long enough to become normal, to establish cycles, to create an environment, stable enough that if we could have stood on those ancient shores, we might have felt something like permanence, might have believed this water would flow forever. But permanence is an illusion. Planets change, atmospheres thin, oceans vanish, and Mars, lacking something crucial that Earth possesses, began a slow decline from ocean world to desert world, from possibility to fossil. What was missing? What single factor determined that Earth would bloom with life while Mars would sleep in silence? The question hangs in the thin Martian air, waiting for an answer. The same air that Zhurong samples with each passing sol, measuring its pressure, its composition, its temperature. Air that was once thick enough to keep water liquid, but is now so thin that water boils at room temperature, unable to maintain the liquid state that chemistry needs to become complex, to become alive. Somewhere in Zhurong's data, in the radar, echoes and chemical analyses, in the careful measurements of dust and stone, lies part of the answer. And that answer begins not with water, but with something invisible, something that surrounds our Earth every moment, but that we notice only in its absence. A shield, an invisible ocean of magnetism that wraps around our world and pushes back against the solar wind. Mars once had this shield too, and then, for reasons we're only beginning to understand, it lost it. That loss changed everything. That single change transformed an ocean world into the red desert we see today. But that part of the story unfolds next in the invisible realm, where planets generate their protection against the void, where we'll discover what happens when that protection fails, and why Earth still sings with life while Mars lies silent, waiting for questions we're only now learning to ask. The Tianwen-1 orbiter circles Mars every 7 hours, tracing an elliptical path that brings it as close as 265 kilometers to the surface, then swings it out to 12,000 kilometers above. From that vantage point, sweeping across the red planet in graceful arcs, its magnetometer samples something invisible, something most of us never think about. But that determines whether a world can hold on to its breath. Magnetic fields. The whisper of iron in a planet's core, spinning, generating currents that ripple outward through rock and air and into space itself. Earth has one, a strong one. It wraps around our world like an invisible ocean, deflecting charged particles from the sun, creating auroras at the poles, and doing something far more crucial, keeping our atmosphere from being slowly, relentlessly stripped away into the void. Mars once had one too. And then 4 billion years ago, give or take a few 100 million years, something changed. The magnetic field weakened, flickered, and died. What remained is what Tianwen-1 measures now, scattered patches of magnetism frozen into ancient rocks, fossil fields, that tell of a time when Mars was protected when it had a chance. The data streams down in careful pulses, each measurement adding to a map that grows more detailed with every orbit. What emerges isn't uniform. The southern highlands of Mars, the oldest terrain on the planet, show strong magnetic signatures, in places strips and patches where ancient lava flows cooled and locked in the orientation of the magnetic field that existed at that moment. Scientists call these magnetic anomalies, though there's nothing anomalous about them once you understand what they represent. They're memories. Frozen moments from a time when Mars still generated its own protection. The northern plains where Zhurong rests show almost nothing. The magnetic field there is perhaps 1% as strong as Earth's, barely enough to measure, certainly not enough to matter. This tells us something important about timing. The northern plains are younger geologically speaking. They formed after the magnetic field had already died, after whatever process generated that field in the planet's core had ceased. But what generates a planetary magnetic field? The answer lies deeper than any drill could reach in the molten heart of a world. Earth's core consists of two parts: a solid inner core of crystallized iron and nickel, and a liquid outer core where these metals flow in currents driven by heat from the planet's interior. As Earth rotates, these currents organize themselves into a dynamo, a self-sustaining system that converts motion into magnetism. The faster the rotation, the more heat available, the stronger the magnetic field becomes. Mars has a core too, roughly half the diameter of Earth's core, rich in iron and sulfur. But it's smaller, and small things cool faster. By the time Mars was 1 billion years old, perhaps younger, its core had cooled enough that the outer portion began to solidify. The convection currents that drove the dynamo weakened, became irregular, and eventually stopped. The magnetic field didn't vanish instantly. It faded over millions of years, growing weaker and more patchy, until only those frozen remnants and ancient rocks remained. Think about what this means. For the first few 100 million years of its existence, Mars had protection. The solar wind, that constant stream of charged particles flowing outward from the sun at 1,000,000 miles per hour, couldn't reach the Martian atmosphere directly. It hit the magnetic field, first was deflected around the planet, creating a cavity in space called a magnetosphere. Inside that cavity, the atmosphere could accumulate, could grow thick enough to trap heat to allow liquid water to exist on the surface. But when the field died, the protection vanished. Suddenly, cosmically speaking, the solar wind had direct access to the upper atmosphere. And here's what happens when charged particles from the sun collide with atmospheric molecules: they transfer energy. Some molecules get knocked into higher, faster orbits. Some gain enough energy to escape Mars's gravity entirely. One by one, molecule by molecule, the atmosphere began to leak away into space. This process has a name: atmospheric sputtering. NASA's MAVEN mission, which arrived at Mars in 2014, was specifically designed to measure this loss. It found that Mars is still losing atmosphere today, roughly 100 grams per second. That sounds like nothing like the weight of a candy bar every second drifting away into darkness. But over 4 billion years, it adds up. Calculations suggest that Mars may have lost an atmosphere equivalent to what Earth has now, maybe more, blown away by the solar wind like dust from a forgotten shelf. Here's where the story becomes both beautiful and terrible. That thick early atmosphere is what kept the water liquid. Atmospheric pressure determines the boiling point of water. On Earth at sea level, water boils at 100 degrees Celsius. But raise the altitude, reduce the pressure, and the boiling point drops. At the summit of Mount Everest, water boils at just 68 degrees Celsius. On Mars today, with atmospheric pressure, less than 1% of Earth's water can't exist as a liquid at all. It either freezes solid or boils directly into vapor, a process called sublimation. But with a thick atmosphere with pressure similar to Earth's Martian water, could have remained liquid across a wide range of temperatures. Those ancient oceans Zhurong's data revealed could have persisted, could have developed currents and chemistry, and all the complex interactions that occur when water moves and mixes and touches different minerals in different ways. The timeline matters here. The magnetic field died roughly 4 billion years ago. The oceans persisted until perhaps 2.9 billion years ago, maybe more recently in some locations. That's 1 billion years, where Mars had liquid water, but no magnetic field, 1 billion years of slow atmospheric loss. It wasn't instant. It wasn't catastrophic in human terms. If we could have stood on ancient Mars and watched, we wouldn't have noticed the atmosphere thinning from one year to the next, or even from one millennium to the next. The change was geological, astronomical, measured in millions of years rather than lifetimes. But it was inexorable. Each passing century, a little less air. Each millennium, a slightly lower boiling point for water. Eventually, gradually, the oceans began to freeze from the surface down during the long Martian winters. And when they melted in summer, some portion of the liquid water evaporated into the thinning air, rose high enough to be struck by solar wind particles, and was split into hydrogen and oxygen. The hydrogen lighter escaped into space. The oxygen either escaped as well or bonded with iron and Martian rocks, creating the rust-red oxides that give the planet its color. This is why Mars is red. Not because it was always red, but because it lost its protection, lost its air, and its water broke down into constituent elements that either vanished or painted the surface in shades of oxidation. Earth could have followed the same path. Our planet is larger, its core, hotter, and more active, but there's no guarantee that our magnetic field will persist forever. In fact, we know it doesn't stay constant. The geological record shows that Earth's magnetic field has reversed many times, north becoming south, and south becoming north in irregular intervals, averaging every few 100,000 years. During these reversals, which can take thousands of years to complete the field, weaken significantly, sometimes dropping to just 10% of its normal strength. The last reversal occurred 780,000 years ago. We're overdue statistically speaking, though. Planetary processes don't follow statistics the way coin flips do. What would happen if Earth's field weakened or vanished? Would we face the same fate as Mars? Not immediately, not quickly. Earth has advantages Mars lacked. We're closer to the sun, which means more solar energy to drive atmospheric circulation and replenish volatiles through volcanic activity. We're larger with stronger gravity that holds atmosphere more tightly. And we have life billions of years of photosynthetic organisms that constantly replenish oxygen in the atmosphere. But we're not invulnerable. There's a region above the South Atlantic Ocean called the South Atlantic Anomaly, where Earth's magnetic field is already unusually weak, about 30% weaker than in other regions. Satellites passing through this area experience higher rates of radiation damage. Astronauts on the International Space Station receive increased radiation doses when orbiting through this zone. It's a small preview of what a wider magnetic weakening might entail. Scientists study this anomaly, carefully measuring how it changes from year to year, because it might represent the beginning of a magnetic reversal, or it might just be a temporary fluctuation in the field structure. We don't know yet. Planetary magnetic fields are chaotic systems, sensitive to conditions in the core that we can measure only indirectly through seismic waves and careful analysis of how Earth wobbles as it spins. What we do know what Mars teaches us is that magnetic fields matter. They're not merely scientific curiosities or the cause of pretty auroras. They're fundamental to a planet's ability to maintain an atmosphere, to keep water liquid, to provide stable conditions over the billions of years that complex chemistry needs to become biology. Tianwen-1's magnetometer continues its patient work, mapping field strengths as it orbits, finding those scattered patches of ancient magnetism frozen in southern rocks. Each measurement adds detail to our understanding of when the field existed, how strong it was, how it declined. And Chinese scientists working with international collaborators are building computer models of young Mars, simulating how the dynamo might have operated, what conditions in the core led to its eventual shutdown. These aren't merely academic questions. If humanity ever hopes to make Mars habitable again, to terraform it as science fiction has long imagined, we'll need to address the missing magnetic field. Some proposals suggest building a giant magnetic shield at Mars L1 Lagrange, point the gravitationally stable spot between Mars and the Sun, where it could deflect solar wind and allow the atmosphere to thicken naturally over centuries or millennia. It sounds like fantasy, but the physics is sound, and Tianwen-1's data helps us understand exactly what strength such a shield would need, what coverage it would have to provide. Other proposals are more modest, creating local magnetic fields around habitats or even entire valleys using superconducting cables, essentially building artificial magnetospheres for human settlements. Again, the data matters. Understanding how atmospheric loss occurs, how it varies with altitude and latitude, helps engineers design effective protection. But perhaps the deepest lesson Mars offers isn't about protection or engineering. It's about fragility. Earth feels permanent, solid, unchanging in human timescales. We breathe air and drink water and watch auroras dance at the poles, and we assume these things will always be. Mars reminds us they won't, that everything depends on conditions maintained by processes, deep underground processes we barely understand that could shift or cease on timescales we can't predict or control. That ancient ocean beneath Jurong's wheels didn't vanish because Mars did something wrong. It vanished because planetary cores cool, because small worlds can't maintain the heat and motion needed to generate protection, because physics is patient and inexorable and doesn't care about potential or possibility. Yet the ice remains hidden beneath dust and stone waiting. That persistence, that refusal to completely vanish, speaks to something beyond physics, to the way matter organizes itself, to the patterns that emerge when chemistry is given time and pressure and the slow work of geology. Water doesn't just disappear, it transforms it, hides it, waits in forms we're only now learning to detect. Those frozen layers that Jurong's radar revealed aren't just scientific data points. They're promises, hints that the story isn't finished, that Mars still holds reserves of what it once possessed in abundance, reservoirs that might, under the right conditions, flow again. Jurong's ground-penetrating radar sends pulses into the Martian soil 40 times per second. Each pulse travels downward at the speed of light, passes through layers of dust and rock and something else, something unexpected, then bounces back. The return signal arrives microseconds later, carrying information encoded in timing and strength, in the subtle ways electromagnetic waves change when they encounter different materials. Water ice reflects radar differently than rock. It has a distinct signature, a particular way of slowing and bending the signal that scientists have learned to recognize. And in Utopia planitia beneath dust that appears bone-dry beneath stones that seem to have never known moisture, that signature appears again and again. Ice. Not at the poles where we expect it, where frost visibly accumulates each winter, but here in mid-latitudes buried beneath the surface, like a secret the desert keeps close. The discovery emerged slowly from data analysis, Chinese scientists poring over thousands of radar profiles, comparing signals, eliminating alternative explanations. What they found suggests ice layers beginning at depths of just 1 to 15 meters, extending downward to 80 meters or more in some locations. Not small pockets or scattered crystals, but continuous layers, sheets of frozen water that could, if melted, flood the surrounding landscape. The implications ripple outward like waves from a stone dropped in still water. If ice exists here in these mid-latitude plains, it likely exists in many other locations across Mars. Previous missions had found ice at high latitudes near the poles, where cold preserves it. But mid-latitude ice is different, more accessible, closer to the equatorial regions, where human missions would likely land, where solar panels generate more power and communication with Earth is more straightforward. This ice tells a story about Mars' recent past, recent in geological terms, meaning the last few million years. Mars's axial tilt, the angle at which the planet leans as it orbits the Sun, isn't stable the way Earth's is. Our planet has the Moon, whose gravitational pull acts as a stabilizer, keeping our tilt steady at about 23.5 degrees. This stability gives Earth consistent seasons, predictable climate patterns averaged over millions of years. Mars has 2 moons, but they're tiny, barely large enough to qualify as moons rather than captured asteroids. Phobos, the larger, is only 22 kilometers across. Deimos, smaller, still measures just 12 kilometers. Together, they provide almost no gravitational stabilization. Mars's axial tilt swings wildly over cycles measured in hundreds of thousands of years, varying from about 15 degrees to 35 degrees or more. When the tilt increases, the polar regions receive more direct sunlight during summer. The ice caps partially sublimate water vapor, rising into the atmosphere carried by winds toward lower latitudes. There, as temperatures drop at night or during winter, the vapor condenses and falls as frost or snow, gradually accumulating over thousands of years. When the tilt decreases again, this mid-latitude ice becomes buried under dust, blown by seasonal winds, protected from sublimation by an insulating blanket of dry regolith. The ice Jurong detected is likely a relic of these climate cycles deposited when Mars' tilt was greater now, hidden beneath dust, that fell during subsequent epochs when the tilt decreased. Computer models suggest the current ice deposits could be between 400,000 and 2 million years old, ancient by human standards, but remarkably young by Martian timelines. Think about what this means for future exploration. Every human needs water, roughly 3 liters per day, for drinking more, for hygiene, food preparation, and growing plants. Launching water from Earth to Mars costs approximately $10,000 per kilogram at current rates. A crew of 4 astronauts on a 2-year mission would need roughly 9 tons of water just for drinking, costing $90 million to transport. But if water already exists on Mars buried a few meters down, suddenly those missions become dramatically more feasible. The technology to extract it already exists in principle. Drilling equipment could penetrate to the ice layer, heating elements could melt it, and pumps could bring the liquid water to the surface. The energy requirements aren't trivial. Melting ice and keeping it liquid in Martian temperatures demands significant power, but they're manageable compared to the impossibility of bringing all necessary water from Earth. And water isn't just water. Through electrolysis running an electric current through liquid water, you can split H2O into hydrogen and oxygen. The oxygen becomes breathable air. The hydrogen can be combined with carbon dioxide from Mars' atmosphere to create methane rocket fuel for the return journey to Earth. One resource ice becomes 3 critical supplies: water, oxygen, and fuel. This concept has a name among mission planners: in situ resource utilization, using what's already on Mars rather than bringing everything from home. NASA's Perseverance rover carries an experiment called MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment, which has successfully demonstrated oxygen production from Martian CO2. It produces about 6 grams of oxygen per hour, enough for a human to breathe for about 10 minutes. Scale that up, combine it with water extraction, and you have the foundation of a self-sustaining presence. But there's a common misconception worth addressing here. Many people, when they hear about Martian ice, imagine something like Antarctica, vast glaciers, and ice sheets visible from space. Mars's ice isn't like that, not in these mid-latitudes. It's buried invisible from the surface, mixed with dust and rock in proportions that vary from place to place. Some layers might be pure ice, clear as glass if you could see them. Others are dusty ice soil particles suspended in frozen water, creating a substance more like permafrost than glacier ice. Earth has permafrost, 2 vast regions in Siberia, Alaska, northern Canada, where ground remains frozen year-round. Scientists studying Martian ice often compare it to terrestrial permafrost, using techniques developed for one world to understand the other. They've found striking similarities. Both contain ice that preserves materials for extraordinary lengths of time. Both respond to climate changes by advancing or retreating over millennia. Both create distinct landscapes as ice beneath the surface expands and contracts with temperature changes. Those landscapes are visible on Mars if you know what to look for. Polygonal patterns in the soil, created as ice expands during formation and contracts during warming, cracking the surface into geometric shapes. Scalloped depressions, where ice has sublimated from below, causing the overlying material to collapse into dimples and hollows. Small mounds called pingos, formed when pressurized water underground freezes and pushes upward, creating hills that are actually ice cores, covered with a thin veneer of dust and rock. Zhurong photographed some of these features during its traverse. The images show a landscape that appears dead frozen, unchanging, but the subtle topography tells of processes still occurring, ice still shifting in response to temperature changes that span years and decades. Even now, in the cold Martian present, the planet isn't entirely static. It breathes slowly through cycles of freezing and thawing that operate at time scales just beyond human perception. The thermal properties of this ice matter too. Zhurong carries instruments that measure how soil conducts heat, how quickly temperature changes penetrate downward from the sun-warmed surface. Ice, even dusty ice, conducts heat differently than dry regolith. The data shows that regions with subsurface ice maintain more stable temperatures, warming and cooling more slowly than areas without ice. This thermal inertia has practical implications. A habitat built over subsurface ice would benefit from more stable temperatures, requiring less energy for heating and cooling. The ice acts as thermal mass buffering against the dramatic temperature swings that characterize Martian days and nights. But extracting this ice presents challenges beyond just drilling and melting. Mars's low atmospheric pressure creates problems. Heat a container of ice on Mars, and as it melts and starts to warm toward what we'd call room temperature, it begins to boil. Water can't remain liquid at standard, human comfortable temperatures under Martian surface pressure. Any extraction system needs to be pressurized, sealed, carefully managed to keep water in its liquid state. There's also the question of purity. Is this ice clean, or does it contain dissolved minerals, salts, perchlorates, that would make it toxic? Without extensive treatment, Zhurong's chemical analysis instruments have detected perchlorates in Martian soil, compounds containing chlorine and oxygen that form naturally on Mars, but that are harmful to humans in high concentrations. If these perchlorates are dissolved in the ice, any water extracted would need filtration and purification before use. Yet, even with these challenges, the presence of ice transforms Mars from a destination that requires complete self-sufficiency into a world where basic resources exist, waiting to be accessed. It changes the conversation from, how do we bring everything we need, to, how do we use what's already there? That shift, subtle as it seems, represents a fundamental change in how we approach human Mars missions. The Chinese space program has stated ambitions to land humans on Mars by the 2030s or early 2040s. The exact timeline shifts as budgets and technologies develop, but the intention remains clear. And every discovery Zhurong and Tianwen-1 make feeds into planning for those future missions. Where is ice most accessible? Which landing sites offer the best combination of scientific interest and resource availability? How much power would extraction require in different locations with different ice concentrations? These aren't academic questions. They're the practical considerations that determine whether human Mars missions are feasible with current or near-future technology, or whether we need breakthrough innovations in propulsion life support or resource processing first. And there's something profound about the idea of using Martian ice, something that goes beyond practical resource utilization. That ice fell as snow or frost during epochs when Mars's climate was slightly different, when the axial tilt was greater and the polar caps sublimated more readily. It's young geologically speaking, but it's still ancient by human measures, older than our species, older than the genus Homo. It fell and accumulated and was buried. While early hominids were just beginning to walk upright in African savannas, while Earth's ice ages were advancing and retreating, while continents drifted and mountains rose. Now, we're learning to find it, to map it, to plan how we might melt it and drink it and use it to sustain a presence on another world. There's a poetry in that continuity, in the idea that frozen water deposited by Martian climate cycles hundreds of thousands of years ago might someday quench the thirst of human explorers, might become the oxygen they breathe and the fuel that brings them home. Do you ever wonder what that first sip of Martian water will taste like? Not water brought from Earth in carefully sterilized containers, but water that was part of Mars, that fell from Martian skies and lay frozen in Martian soil for ages beyond counting. Someone will drink it someday, will be the first human to consume something that came entirely from another world. The moment will probably be documented, photographed, broadcast across the solar system, with the slight delay that light speed imposes. But the taste, the actual experience of that water that will belong only to the person experiencing it, unique and private and impossible to fully convey. Perhaps it will taste of minerals of the soil it's soaked through. Perhaps it will taste surprisingly clean, purified by its long freeze. Or perhaps it will taste like water, always taste neutral and necessary, remarkable only in its absolute familiarity despite its alien origin. Water is water, whether it falls as rain in Seattle or snow on Olympus Mons. The chemistry doesn't change. Two hydrogen atoms, one oxygen bonded at an angle of 145 degrees. Universal, constant. A molecule that exists on every world where temperature and pressure allow. It taking the same form, whether it's formed from stellar fusion products, or volcanic outgassing, or comet impacts. That universality is part of what makes the search for life beyond Earth so compelling. Life as we know it requires liquid water. Every organism on Earth, from the simplest bacterium to the largest whale, needs water for its biochemistry. And while we can imagine exotic biochemistries that might use other solvents, ammonia perhaps, or methane, we have no examples of such life, no proof it's possible. Water is what we know. Water is what we look for. And Mars has water. Not flowing rivers anymore, not open oceans, but water, nonetheless frozen and hidden and waiting. That presence keeps the question alive. Could life have arisen during Mars's wetter past? Could it persist now in pockets of liquid water beneath the surface in aquifers, warmed by geothermal heat, in films of brine that resist freezing even in Martian cold? The ice Jurong found doesn't answer those questions, but it reminds us they're worth asking, that Mars isn't as dead as it appears, that beneath the rust and dust, beneath the silence and the thin cold air reservoirs remain. Reservoirs of possibility. Reservoirs that future missions will tap, will analyze, will perhaps find within traces of chemistry more complex than frozen water alone. But that search, that question of whether Mars ever held life or holds it still in hidden refuges, requires understanding not just where water is, but what else exists in Martian soil, what chemistry shaped these rust-red plains, what compounds lurk in dust that appears uniform but holds secrets in its composition. Jurong carries a laser on its mast, a device called a laser-induced breakdown spectrometer, pointed at a rock fire, a pulse of focused light, and for a fraction of a second, the target surface vaporizes, becoming a tiny plasma cloud hot enough to make atoms glow. Different elements emit light at different wavelengths when excited this way. Measure that light spectrum, and you can determine what the rock is made of, what chemicals have soaked into it over millions of years, what stories the chemistry tells. The rover has analyzed dozens of samples across Utopia Planitia, each reading adding to a chemical portrait of Mars that grows stranger and more complex the more we learn. The soil isn't uniform. It isn't simple. It's a mixture of minerals that shouldn't exist together under Earth conditions, compounds that tell of processes we're still struggling to understand. Iron oxides dominate as expected. This is what gives Mars its red color rust, in various forms coating nearly every surface. But the specific types of iron oxide matter. Jurong detected hematite, magnetite, and megamite, 3 different crystalline arrangements of iron and oxygen that form under different conditions. Hematite is reddest, the mineral responsible for Mars' distinctive hue. It forms in the presence of water and oxygen over long periods. Magnetite is black magnetic, typically created at high temperatures. Megamite sits somewhere between, often forming when magnetite is exposed to oxidizing conditions. The presence of all three together suggests a complex history. The soil has been heated, cooled, wetted, dried, oxidized, and reworked countless times. Each process leaves its signature in the mineral assemblage, and scientists reading those signatures can reconstruct sequences of events that occurred billions of years ago, can trace the transformation of Martian surface materials through epochs of change. But iron oxides are just the beginning. Jurong's spectrometer also detected significant concentrations of perchlorate salts containing chlorine and oxygen in a particular molecular arrangement. On Earth, perchlorates are relatively rare, found in certain desert environments and in some industrial settings. On Mars, they appear to be ubiquitous, present in soil samples from every landing site we've examined. These perchlorates are both promising and problematic. They're promising because perchlorate salts lower the freezing point of water dramatically. Pure water freezes at 0 degrees Celsius, but water with dissolved perchlorates can remain liquid down to -70 degrees or lower, depending on concentration. This means that even in Mars' current cold state, liquid brines might exist in certain locations in pockets where perchlorates have concentrated and where geothermal heat or sunlight provides enough energy to keep temperatures above the brine's freezing point. Such brines could potentially support microbial life, extremophile organisms, adapted to high salinity and chemical conditions that would kill most Earth organisms instantly. We know such extremophiles exist on Earth. Halophilic archaea thrive in salt concentrations that would desiccate normal cells. They have been found in salt mines in the Dead Sea, in brine pools at the bottom of the Mediterranean. If life ever arose on Mars, descendants might persist in similar brines hidden in fractures in rock or in aquifers deep underground, where liquid water, however salty, still flows. But perchlorates are also problematic because they're toxic to humans. Ingesting perchlorates disrupts thyroid function, interfering with iodine uptake and hormone production. The Martian soil, that rust-red dust that gets everywhere, that would coat every surface and seep into every seal, contains compounds that we'd need to carefully filter and remove before using water or growing food. Any agricultural system on Mars would need to either remove perchlorates from soil or break them down, chemically transforming them into harmless chlorides and oxygen. Interestingly, that decomposition reaction is possible and even useful. Certain bacteria on Earth can metabolize perchlorates, using them as a source of oxygen for respiration. Scientists are studying whether such bacteria could be adapted to Martian conditions, creating bioreactors that clean soil while producing oxygen as a byproduct. It's an elegant solution if it proves viable, turning a toxin into a resource through biological processing. Beyond perchlorates, Jurong detected silicates, the rock-forming minerals that make up most of Earth's crust as well. Silicon dioxide, feldspars, pyroxenes, all common on both worlds. But the proportions differ. Mars has more magnesium-rich minerals and fewer aluminum-rich minerals than Earth's continental crust. This tells geologists that Mars never developed plate tectonics, the way Earth did. Never had the recycling of crust through subduction zones that concentrates aluminum into continental material. The volcanic history is written there too, in the specific types of minerals present. Mars was volcanically active for much of its early history, perhaps into relatively recent times, geologically speaking. The volcanoes produce basaltic lava, similar to what erupts in Hawaii or Iceland on Earth, magma rich in iron and magnesium. That lava cooled into rock, then weathered over billions of years into the soil Jurong samples now. But weathering on Mars is different from weathering on Earth. Without liquid water, without life, without the organic acids that plants and microbes produce, Martian weathering is primarily physical rather than chemical. Temperature changes crack rocks, freeze-thaw cycles in ice-containing regions, pry stones apart, wind erosion slowly abrades surfaces. The result is soil that's more angular, less rounded than Earth. soil particles that haven't been tumbled in rivers or ground down by glaciers or processed through the digestive systems of countless organisms. There's another compound that appeared in Zhurong's data, one that sparked particular interest among astrobiologists: hydrated minerals, specifically sulfates and phyllosilicates. These minerals contain water molecules locked into their crystal structure water that was present when the minerals formed and that remains chemically bound within them. On Earth, such minerals form in specific environments, often where water was present for extended periods, where lakes evaporated, leaving dissolved minerals behind, or where groundwater percolated through rock and altered its chemistry. The sulfates suggest ancient water with specific chemistry water that was slightly acidic, that had dissolved sulfur compounds from volcanic gases or from sulfur-bearing rocks. The phyllosilicates clay minerals suggest a different environment, neutral pH water, that persisted long enough to chemically alter volcanic rock into clay. Both types of minerals exist in Utopia, Planitia, sometimes in the same sample, suggesting that water chemistry changed over time, that different conditions prevailed in different epochs, or even in different microenvironments within the same general region. This layering of different mineral types, this record of changing conditions, is precisely what geologists hope to find when searching for habitable environments. Life doesn't require a single perfect set of conditions maintained forever. It requires variability changes that create chemical gradients, energy sources that organisms can exploit. A world that was always exactly the same would be chemically dead reactions running to equilibrium and stopping. But a world that cycles between wet and dry, between acidic and neutral, between oxidizing and reducing conditions, that world offers opportunities for chemistry to become complex, to explore the space of possible reactions, and find the pathways that lead eventually, improbably, to self-replicating systems. Think about what we're really describing here. Mars's soil isn't dirt. It's not the living, breathing mixture of minerals and organic matter and countless microorganisms that we call soil on Earth. It's regolith broken rock, chemically altered but biologically barren as far as we can determine. Yet it contains the ingredients life needs: carbon and atmospheric CO2, hydrogen and water, ice, nitrogen in the thin atmosphere, phosphorus and sulfur in minerals. The elements are there. The energy sources exist: sunlight and chemical gradients and possibly geothermal heat in some locations. What's missing? Not ingredients, not energy. What's missing might simply be time, or rather the continuation of time under suitable conditions. Mars had perhaps 1 billion years when conditions were wet enough, warm enough, stable enough for complex chemistry to potentially cross the threshold into biology. Earth had a similar window and life emerged. The fact that we exist, that Earth's surface teems with organisms, proves that the transition from chemistry to biology is possible, that given the right conditions and enough time, matter can organize itself into patterns that grow, reproduce, evolve. Did it happen on Mars? We don't know. The chemistry is suggestive but not conclusive. We've found the stage where the play might have occurred, the theater with its props and lighting, but we haven't yet found evidence of the performance itself. No fossils, no biomarkers, no organic molecules that clearly indicate biological origin. NASA's Perseverance rover, currently exploring Jezero crater on the other side of Mars, is specifically designed to look for such evidence. It's collecting samples that a future mission might return to Earth for detailed analysis in laboratories far more sophisticated than anything we can send to Mars. The Chinese space program has announced similar ambitions plans for a sample return mission that would land, gather carefully selected rocks and soil, and launch them back toward Earth for retrieval. These missions represent the next phase of Martian exploration, moving beyond remote sensing and in situ analysis toward bringing pieces of Mars home, where we can apply every analytical technique we possess, where we can search for the subtle chemical and structural signatures that biology leaves behind. Because if Mars ever had life, even simple microbial life, it should have left traces. Fossils, perhaps, though fossilization requires specific conditions. And microbial fossils are notoriously difficult to identify, with certainty even on Earth. Chemical signatures, more likely specific isotope ratios, or organic molecules or mineral textures that biological processes produce. But there's a paradox here, one that scientists working on Mars missions navigate carefully. The more we search for life, the more we risk contaminating Mars with Earth life, making it harder to determine what's truly Martian and what's terrestrial hitchhiker. Every spacecraft sent to Mars is carefully sterilized, heated to temperatures that kill known organisms assembled in clean rooms with filtered air and stringent contamination control. But sterilization is never perfect. Some bacterial spores survive extreme conditions dormant and waiting. And if such spores landed on Mars and found against all odds some pocket of warmth and moisture where they could revive and grow, we'd have inadvertently created the very life we're searching for. This concern, called forward contamination, shapes mission planning in fundamental ways. Certain regions of Mars are designated as special regions, areas where liquid water might currently exist, and where Earth organisms, if introduced, might potentially survive and reproduce. Rovers are programmed to avoid these regions unless they've been sterilized to extreme standards. The goal is to keep Mars as pristine as possible, to preserve any native Martian biology from competition or contamination by Earth organisms, and to ensure that if we do find life, we can be confident it's genuinely Martian. It's a form of planetary protection, a recognition that we have responsibilities beyond just scientific curiosity, that Mars belongs not just to us, but to itself, to its own history and potential future. Whether that future includes Earth-descended life is a question for later, for debates about terraforming and colonization that won't be resolved for decades or centuries. For now, the scientific community largely agrees that caution is warranted, that we should know what Mars is before we change it into something else. Jurong's chemical analyses contribute to this understanding mapping, where different minerals exist, where conditions might be more or less amenable to contamination, where future missions should focus their searches or exercise extra caution. Every data point helps refine models of Martian chemistry, helps distinguish between what's possible and what's probable, what's ancient history, and what might still be occurring in hidden places we haven't yet explored. And the chemistry continues to surprise us. Recent analysis of Jurong's data revealed chlorine compounds beyond just perchlorate's complex molecules that might form through atmospheric chemistry, through reactions between surface minerals and the thin Martian air. On Earth, chlorine chemistry is deeply intertwined with life. Organisms produce chlorinated compounds for various purposes, from chemical defense to metabolism. The presence of complex chlorine chemistry on Mars doesn't indicate life, but it shows that chemistry there is active, ongoing, that Mars isn't a dead rock, but a world where reactions still occur, where the surface and atmosphere interact in ways we're only beginning to map. There's also the question of organic molecules, carbon-based compounds that might indicate past life, or might simply result from non-biological processes. Mars receives a constant rain of organic material from space carbon-rich meteorites and cosmic dust settling on the surface. These organics should be detectable, should accumulate over time. Yet instruments on various missions have struggled to find them, or found them only in trace amounts far less than models predict should exist. The leading explanation involves those same perchlorates we discussed earlier. At high temperatures, perchlorates can break down organic molecules, destroying them before instruments can detect them. This has complicated the search for Martian organics, required scientists to develop new techniques, new ways of analyzing samples that avoid the destructive heating that traditional methods employ. It's a reminder that exploring another world isn't straightforward, that techniques developed for Earth conditions don't always transfer cleanly to alien environments, that every answer brings new questions, new complications to navigate. The soil seems simple, just rust-colored dust and broken rock. But that simplicity is deceptive. Within that dust are minerals that formed under different conditions than any we know on Earth today. Chemicals that exist in combinations we rarely see a record of planetary evolution that spans billions of years and includes epochs of warmth and cold, wet, and dry volcanic fury and gradual decline into the cold desert state that persists now. Reading that record requires patience, requires accumulating data point by data point, sample by sample, comparing findings from different missions and different locations to build a coherent picture of Martian chemistry and how it came to be. And within that picture might lie clues not just to Mars' past, but to how planets evolve, how chemistry becomes complex, how common or rare the conditions for life might be throughout the universe. But chemistry alone doesn't tell the full story of a living world. Even with all the right ingredients, even with water and energy and complex molecules, life requires dynamics, requires change and movement cycles that break stasis and create opportunities. On Earth, weather drives such cycles, wind and rain, redistributing materials, seasons changing conditions. Mars has weather too thinner and subtler than Earth's, but weather nonetheless patterns that emerge when sunlight warms different latitudes differently, when the thin air responds with motion, when dust rises and swirls in patterns that seem alive, even though they're purely physical, purely mechanical responses to heat and pressure and the ancient mathematics that governs how gases flow. Zhurong's weather station records data every few minutes, measuring wind speed and direction, air temperature, atmospheric pressure, humidity levels so low they barely register. Most readings show calm conditions, winds barely strong enough to stir the dust, but sometimes the anemometer spins suddenly faster. The pressure drops momentarily, and the cameras capture something moving across the Martian plain. Dust devils, vertical columns of spinning air made visible by the dust they carry upward, sometimes reaching heights of several kilometers. They dance across the landscape like living things, like spirits of wind given temporary form, though they're purely physical phenomena, thermodynamic responses to uneven heating of the surface. They occur on Earth too in deserts where bare ground heats quickly under direct sunlight. Arizona, the Sahara, the Atacama Desert all host dust devils during hot afternoon hours. But Martian dust devils are different, larger and more numerous than their terrestrial cousins formed under conditions that seem too gentle to produce such dramatic phenomena. Mars's atmosphere is thin, less than 1% the density of Earth's air at sea level. You might think this thinness would make weather impossible, that winds would be too weak to matter. But pressure isn't the same as movement. Martian winds can reach speeds exceeding 100 kilometers per hour during certain seasons. And while they exert far less force than equivalent Earth winds due to the low density, they're more than capable of lifting and transporting dust. The process begins with differential heating. Sunlight strikes the surface, warming darker materials more than lighter ones, creating temperature differences across small areas. Warm air rises, cooler air flows in to replace it. And if conditions are right, this circulation organizes itself into a vortex, a spinning column that becomes self-reinforcing. As air spirals upward in the center, it accelerates, pulling more air inward at the base, creating lower pressure at the core that draws in even more surrounding air. On Earth, similar processes form tornadoes, though those involve vastly more energy and much larger pressure differences. Dust devils are gentler, smaller, though still impressive when you witness one crossing a desert landscape. On Mars, they're routine happening somewhere on the planet at almost every moment during daylight hours. Zhurong documented hundreds of dust devils during its operational period, some passing within meters of the rover, close enough that instruments detected the pressure drop and temperature change as the vortex swept past. The largest appeared to be about 100 meters in diameter at the base, with visible columns extending upward until they faded from view in the thin atmosphere. Scientists estimate some may reach 5 kilometers high or more, though the upper portions are too diffuse to see clearly in images. These wind phenomena serve a function that mission planners didn't fully appreciate until early Mars rovers began experiencing it. They clean solar panels. Dust accumulates on horizontal surfaces on Mars, settling out of the air during calm periods, coating everything in a thin layer of fine particles. Over weeks or months, this dust blocks sunlight from reaching solar panels, reducing power generation, threatening to end missions prematurely. But dust devils sweeping across the landscape create enough turbulence to dislodge accumulated dust, lifting it back into the air and leaving surfaces cleaner than before. The Spirit and Opportunity rovers, which landed on Mars in 2004, were designed for 90-day missions, but operated for years, partly because dust devils periodically cleaned their solar panels, these cleaning events sometimes restoring power generation to near original levels. The effect isn't entirely reliable. Some rovers get cleaned frequently, others rarely. It depends on location season, the specifics of local wind patterns. But it represents a form of environmental cooperation, the planet itself, helping extend missions beyond their planned duration, as if Mars wants to be studied, wants its stories told. Zhurong experienced several cleaning events during its traverse, sudden increases in available power that corresponded with weather station data showing dust devil passages. Engineers monitoring the rover's health from Earth, watching telemetry arrive after the 11-minute light speed delay, saw power levels jump and knew a dust devil had swept past, had performed maintenance that no human controller could have commanded or predicted. There's something almost alive about these wind patterns, the way they respond to heating and cooling, the way they organize themselves into coherent structures that persist for minutes or hours before dissipating. They're not alive, of course. They're no more conscious than waves on an ocean or flames in a fire. But they exhibit behaviors that feel purposeful movements, that seem deliberate patterns that repeat with variation, like improvisation within a theme. The larger atmospheric patterns that spawn dust devils are equally fascinating. Mars has seasons caused by its axial tilt, just as Earth's seasons are. But Martian seasons are complicated by the planet's elliptical orbit. When Mars is closest to the Sun in the southern hemisphere's summer, it receives about 40% more sunlight than when it's farthest away during northern summer. This asymmetry creates dramatic differences between hemispheres. Southern summers are shorter but more intense. Northern summers are longer but milder. These seasonal changes drive global wind patterns. As the southern hemisphere warms during its summer, the polar ice cap sublimes, releasing carbon dioxide into the atmosphere. The atmospheric pressure across the entire planet increases by about 25%. This additional gas must flow somewhere, spreading northward, creating winds that persist for months. Then, as southern winter arrives and northern summer begins, the flow reverses. CO2 freezes out at the southern pole, pressure drops, and winds blow southward, returning the atmospheric mass to balance the books. This breathing of the atmosphere, this annual cycle of pressure rising and falling, was one of the first clear indicators that Mars has active weather, rather than a static, dead atmosphere. Early missions measured these pressure changes, tracked how they varied with location and season, and built models of atmospheric circulation that matched observations. The models showed jet streams at high altitudes, Hadley cells similar to Earth's tropical circulation, and complex interactions between surface topography and wind flow. Mars has enormous volcanoes and deep canyons that disrupt atmospheric flow, creating turbulence and local weather patterns. Olympus Mons, the largest volcano in the solar system, stands 21 kilometers above the surrounding plain, tall enough that its summit pokes through much of the atmosphere. Winds flowing around this massive obstacle create vortices, and standing waves, persistent patterns that exist whenever certain wind directions prevail. Valles Marineris, a canyon system stretching 4,000 kilometers along the Martian equator, funnels winds through its length, accelerating them like air through a venturi tube. During certain seasons, winds in the canyon can reach speeds that would qualify as hurricanes on Earth. though again the actual force exerted is much less due to the thin atmosphere. But there's a common misconception worth addressing. Many people, when they hear about Martian wind speeds exceeding 100 kilometers per hour, imagine destructive storms like hurricanes or tornadoes on Earth. Science fiction has reinforced this image with scenes of astronauts battling fierce winds that threaten to topple equipment or blow people away. The reality is gentler. A 100-kilometer-per-hour wind on Mars exerts roughly the same force as a 10-kilometer-per-hour breeze on Earth. You could stand in it comfortably. It wouldn't knock you over or tear at your clothing, though it would certainly fill the air with dust-reducing visibility and coating everything in fine particles. The dust itself is the real concern, not the wind that carries it. Martian dust is extraordinarily fine particles, averaging just 3 micrometers in diameter, small enough to remain suspended in the air for hours or days after winds cease. These particles are also irregular and abrasive, like tiny shards of broken glass. They work their way into seals, abrade moving parts, coat optical surfaces, and could potentially pose health risks to humans if inhaled in sufficient quantities. During large dust storms, which can occasionally grow to encompass the entire planet, the dust becomes so thick that sunlight barely penetrates to the surface. Solar-powered rovers must shut down conserving battery power, waiting for the storm to clear. The Opportunity rover survived many such storms during its 15-year mission, but finally succumbed to one in 2018. When the dust cleared after months, the rover didn't respond to wake-up commands. Its solar panels had been coated too thoroughly, or some critical system had failed during the long darkness. Either way, its mission ended not with a dramatic failure, but with silence, with ceasing to respond, with becoming another artifact on the Martian surface. Zhurong, aware of this history, was designed with dust mitigation in mind. Its solar panels have a coating that resists dust adhesion to some degree. Its moving parts are sealed more carefully than earlier rovers, and mission planners scheduled its landing for a season when large dust storms are less common, giving it the best chance to complete its primary mission before potentially encountering storm conditions. The rover's cameras captured remarkable footage of Martian weather in action. Time-lapse sequences show clouds forming in the early morning, thin wisps of water, ice crystals condensing in the cold pre-dawn air, then sublimating as the sun rises and warms the atmosphere. These clouds are different from Earth's clouds, thinner and more ephemeral, existing only in the coldest parts of the night and morning, before vanishing as if they never were. Other sequences show dust storms on the horizon walls of suspended particles, moving across distant plains, blurring the boundary between ground and sky. The storms advance with a kind of inevitability, reshaping the visible landscape, obscuring landmarks, creating a world that exists only in shades of orange and brown dimensions, reduced to vague shapes in perpetual twilight. There's beauty in these images, a stark aesthetic of minimalism and movement of a world defined by emptiness, and the few things that move within that emptiness: wind, dust, light, the basic elements of weather stripped to their essentials, performing without the complications that life and liquid water add to terrestrial meteorology. Scientists study these weather patterns not just for their intrinsic interest, but for practical reasons related to future human missions. Understanding Martian weather helps predict when dust storms might occur, which seasons offer the clearest skies, which regions experience the calmest conditions. This information feeds into landing site selection, mission timing, habitat design. A Mars base would need to weather dust storms, literally and figuratively. Habitats would need filtered air intakes to keep dust out of living spaces. Solar panels would need regular cleaning, either manual or automated. Communication equipment would need to function during periods of reduced visibility. And humans would need to cope psychologically with weeks or months of limited outdoor activity during severe storms, times when going outside would be inadvisable due to reduced visibility and heavy dust loading. But there's also a strange comfort in Martian weather. A reminder that the planet isn't completely alien, that it shares fundamental processes with Earth, even if the details differ. Both worlds have seasons, winds, clouds, storms. Both experience weather that varies from place to place and time to time. This commonality suggests that human intuitions about weather, developed over lifetimes of experiencing Earth's atmosphere, might partially transfer to Mars, that meteorology skills learned on one world might help predict conditions on another. The mathematics underlying atmospheric circulation is the same. The Navier-Stokes equations that describe fluid flow on Earth apply equally to Mars's thin air. The thermodynamics of heating and cooling, of phase changes between solid and gas, of pressure gradients driving wind, all these principles are universal, determined by physics rather than planetary identity. Yet, the outcomes differ dramatically. Earth's thick atmosphere smooths temperature extremes, transports heat from equator to poles, distributes moisture across continents. Mars's thin atmosphere can't do these things effectively. Temperature differences between day and night, between equator and poles, between summer and winter are more extreme. The daily temperature range at Zhurong's landing site varies from about -20 degrees Celsius at the warmest to -100 degrees. At the coldest, a swing of 80 degrees within a single sol. No Earth location experiences such extremes. Even the most extreme terrestrial climates, Antarctic winter or Saharan summer, don't approach Martian temperature variability. This presents challenges for any equipment or organisms trying to persist on Mars. Materials expand and contract with temperature changes. Seals that work at one temperature fail at another. Chemical processes that are fast when warm become glacially slow when cold. Life, were it to exist on Mars, would need to cope with these swings, would need either to find buffered environments where temperatures remain relatively stable, or to develop dormancy strategies that allow survival across the full temperature range. Earth microbes show that such strategies are possible. Bacterial spores can survive being frozen, can endure temperatures that would kill. Active cells can remain dormant for years or centuries before reviving when conditions improve. But dormancy has limits. The longer an organism remains inactive, the greater the chance of accumulated damage from radiation, from slow chemical degradation, from the simple passage of time. Mars's surface receives far more radiation than Earth's surface due to the lack of magnetic field and thin atmosphere. Cosmic rays and solar particles strike the ground, directly breaking molecular bonds, creating reactive chemicals, damaging DNA or its analogs. Any surface life would need extraordinary radiation resistance, or would need to exist underground, shielded by meters of rock or ice. Perhaps that's where Martian life hides, if it exists at all. Not on the windswept surface where Zhurong rolls and dust devils dance, but deep below, in aquifers where liquid water might still flow, in cavities where geothermal heat keeps temperatures above freezing, in places where the wild swings of surface weather never penetrate, where conditions have remained stable for billions of years, long enough for chemistry to find its own slow path toward complexity. But to understand whether such refuges exist, whether the deep interior of Mars offers sanctuary that the surface denies, we need to look beyond weather and chemistry, beyond the immediate environment that rovers sample, toward the patterns that emerge when we step back, when we observe how the planet changes not just day to day, but season to season, how the frozen poles advance and retreat in rhythms, measured not in sols, but in years, how ice and dust trade places in cycles that have persisted since before humans existed, since before Earth even knew it had a companion in the sky, who once long ago might have been much more similar to home than the cold desert it has become. Tianwen-1 has orbited Mars through more than 2 complete Martian years, now watching from above as the planet wheels through seasons that stretch nearly twice as long as Earth's. A Martian year contains 687 Earth days, almost 2 of our years, compressed into one of theirs. And during that long circuit around the sun, the polar ice caps grow and shrink in rhythms that have persisted for millions of years. From orbit, the cameras capture these changes in sequences that compress months into seconds. The southern ice cap, brilliant white against rust-red terrain, expands during southern winter until it covers an area larger than Antarctica. Then, as spring arrives and temperatures rise, it retreats, sublimating directly from solid to gas, releasing carbon dioxide into the atmosphere. By summer's peak, only a small remnant remains, a core of water ice that never completely disappears, surrounded by layered terrain that records countless cycles of advance and retreat. The northern cap follows its own rhythm, offset by half a year growing, while the southern cap shrinks, retreating, while the southern cap advances. Together, they breathe carbon dioxide back and forth across the planet, a slow exhalation and inhalation that takes a full Martian year to complete. But these aren't the seasons you've experienced. There are no leaves to mark the change, no birds migrating north and south, no spring flowers or autumn harvests. The seasons of Mars are purely physical, thermodynamic, measured in temperature and pressure, and the slow movement of frozen volatiles from one hemisphere to another. Imagine living on a world where seasons last 11 months instead of 3, where winter's darkness extends through what would be nearly a full Earth year before spring finally arrives, where the air itself grows thinner in winter as carbon dioxide freezes out at the poles, then thickens again in spring as that CO2 sublimes back into the atmosphere. These aren't subtle changes. Atmospheric pressure at any given location can vary by 25% or more between seasons, enough that instruments detect it easily enough that it affects weather patterns and dust storm frequency. The seasonal pressure changes were among the first clear signs that Mars has active processes rather than a dead static environment. When the Viking landers touched down in 1976, their pressure sensors recorded daily and seasonal variations that match predictions from atmospheric models. Scientists could explain the daily cycle easily enough: air warming during the day and rising, creating lower surface pressure, then cooling at night and sinking, increasing pressure again. But the seasonal variation required a more sophisticated explanation, one that invoked the massive polar caps and their annual cycle of freezing and sublimation. Think about what this means. A significant fraction of Mars's entire atmosphere, perhaps 20 to 30%, freezes out at the winter pole each year. That's not weather in any terrestrial sense. It's planetary scale chemistry phase changes involving masses of material, measured in trillions of tons, occurring with clockwork regularity, driven by orbital mechanics and solar heating. Earth has nothing comparable. Our polar ice caps grow and shrink with seasons, but they're water ice sitting on solid ground or floating on liquid oceans. The mass of atmospheric gases remains essentially constant. When Antarctic winter arrives, the air gets colder and denser, but it doesn't freeze out of the sky and rain down as solid carbon dioxide snow. Our atmosphere is too warm, our dominant gas nitrogen, with a freezing point of minus 210 degrees Celsius, far colder than any naturally occurring Earth temperature. But Mars's atmosphere is 95% carbon dioxide, which freezes at minus 78 degrees Celsius under Martian pressure conditions. The winter poles easily reach temperatures cold enough for atmospheric CO2 to condense, forming frost that accumulates in layers, building ice caps that can be several meters thick by winter's end. Tianwen-1's cameras have captured this process in detail. Time-lapse sequences show frost appearing first at high latitudes in late summer, thin deposits that come and go with temperature fluctuations. As autumn progresses and the sun's angle decreases, the frost becomes permanent, accumulating night after night, spreading equatorward until by midwinter, it extends to latitudes around 50 degrees, roughly equivalent to the US-Canada border or Northern Europe on Earth. The frost isn't pure. Dust particles in the atmosphere act as condensation nuclei, tiny seeds. around which CO2 ice crystallizes. The result is layered deposits alternating thin sheets of relatively pure ice with dustier layers, creating stratified structures visible in high-resolution images. These layers record variations in dust content from year to year, creating an archive of Martian climate that extends back through countless cycles. Scientists have studied similar layered deposits near the poles, thicker accumulations that represent millions of years of deposition. The layers there vary in thickness and composition, recording epochs when Mars's orbit and axial tilt were different, when climate patterns varied from what we observe today. Reading these layers is like reading tree rings, each one marking a year or a cycle of years. The thickness indicating how much material fell that season, the composition telling what the atmosphere was like when the layer formed. But there's an asymmetry in Martian seasons that makes them more complex than Earth's. Though Mars's orbit is more elliptical than Earth's, and the timing of perihelion, the point of closest approach to the Sun, currently occurs during southern summer. This means the southern hemisphere experiences shorter, more intense summers and longer, colder winters than the northern hemisphere. The effect is dramatic. Southern summer temperatures can reach 20 degrees Celsius or more in favorable locations, warm enough that if pressure were higher, water could exist as a liquid. But southern winter plunges to extremes cold enough that even the tiny amount of water vapor in the atmosphere freezes out, forming thin layers of water ice on top of the carbon dioxide frost. The northern hemisphere's seasons are milder, but longer. Northern summer is cool but extended, giving more time for ice to sublimate. Northern winter is less severe, but lasts longer, allowing frost to accumulate gradually over many months. The result is that the northern polar cap retains a large water ice component year-round, while the southern cap's residual ice is smaller and contains more frozen CO2 mixed with the water ice. These differences create hemispheric variations in atmospheric circulation. During southern summer, the intense heating drives strong updrafts, pulling dust high into the atmosphere. This is when the largest planet-encircling dust storms tend to occur, massive events that can obscure the entire Martian surface for months at a time. The most recent global dust storm occurred in 2018, and Tianwen-1 arrived in time to observe the tail end of the subsequent storm season, capturing images of regional dust storms that covered thousands of square kilometers but didn't achieve global scale. From orbit, these storms appear as expanding patches of orange and brown, obscuring surface features, growing over days from local disturbances into regional events that span multiple climate zones. The orbital instruments track them using multiple wavelengths of light, measuring how much dust the storms carry, how high it reaches, how quickly the storms grow or dissipate. But beneath these dramatic seasonal changes, there's a quieter rhythm, one that operates on much longer time scales. Mars's axial tilt, as mentioned earlier, isn't stable. It varies from about 15 to 35 degrees, over cycles lasting around 120,000 years, with occasional excursions to even higher tilts reaching 40 degrees or more. These variations are driven by gravitational interactions with other planets, primarily Jupiter, whose massive pull tugs at Mars's orbit and orientation over time. When Mars's tilt increases, the poles receive more direct sunlight during summer, causing enhanced sublimation of the ice caps. This releases more CO2 and water vapor into the atmosphere, temporarily thickening it, allowing it to transport more heat from equator to poles, moderating temperature extremes. During these high obliquity periods, Mars becomes slightly more Earth-like, slightly more temperate, though still far too cold and dry for liquid water to persist on the surface in most locations. When tilt decreases, the opposite occurs. The poles receive less summer sunlight, ice accumulates rather than sublimating, and the atmosphere gradually thins as more of its mass becomes locked in polar deposits. Mars becomes even colder and drier than it is today, more hostile to any potential life, more locked in permanent winter. Scientists believe Mars is currently in a moderate phase with tilt around 25 degrees comparable to Earth's 23.5-degree tilt. But it's been much higher and much lower in the recent geological past. And these variations have left their mark in the polar layered deposits and patterns of glaciation, at mid-latitudes in the distribution of subsurface ice, like what Jurong detected in Utopia Planitia. Understanding these cycles helps explain Mars's current state and predicts its future evolution. The planet isn't static. It's slowly changing, oscillating through climate states driven by orbital mechanics. In 50,000 years, Mars's tilt might be 30 degrees, its climate noticeably different from today. In a million years, who knows? The tilt could have reached its upper limit, creating decades-long summers at the poles driving atmospheric processes we can only imagine. There's no life to experience these seasons, no organisms marking time by the return of spring or preparing for winter's arrival. The seasonal changes occur in silence, witnessed only by patient machines and distant observers on Earth who piece together the story from data transmitted across interplanetary distances. What would it be like to live through a Martian year, to watch winter extend for 11 Earth months, ice creeping equatorward, week by week, temperatures dropping slowly until they stabilized at levels that would freeze any Earth organism solid? To endure the darkness, the thin air, the unrelenting cold, knowing that spring was still months away. Then finally, imperceptibly at first, to notice the sun climbing slightly higher, each soul, the frost line beginning to retreat, temperatures rising by fractions of a degree. Spring coming, not as an explosion of life and growth, but as a subtle shift in light and temperature, a gradual lessening of winter's grip. And then summer brief in the southern hemisphere, extended in the north, bringing temperatures that rise towards 0 degrees Celsius, but rarely exceed it, except in the most favored locations. A summer without rain, without clouds, except the thinnest wisps of ice crystals, without the sound of insects or the smell of warming earth. Just stone and dust and the slow sublimation of remaining ice evaporating directly into the air without ever becoming liquid, vanishing as if it never existed. Have you ever experienced a truly silent landscape? A place where sound seems to die before it travels, where your own breathing is the loudest thing you hear? Mars would be quieter still. The thin atmosphere carries sound poorly absorbing high frequencies almost entirely, leaving only low rumbles that travel short distances before fading into nothing. A dust devil passing within meters might produce only the faintest whisper. Thunder, if lightning ever occurred, which it likely doesn't, would be more felt than heard. A pressure wave through air too thin to carry sound the way Earth's atmosphere does. In that silence through seasons that stretch beyond human patience, the planet performs its ancient rhythms. Ice advances and retreats. Dust rises and settles. Pressure climbs and falls, all without witness, without meaning, beyond the physical processes themselves, beauty that exists, whether observed or not, patterns that persist, whether acknowledged or ignored. Tianwen-1 watches and records, translating observations into data, into numbers that represent temperatures and pressures and albedos quantities that scientists analyze and compare and use to refine models of Martian climate. But behind the numbers lie the phenomena themselves, the actual ice crystals forming in the darkness of polar night, the actual dust grains rising on thermal currents and settling again, when winds cease the actual photons of sunlight, striking the surface and warming it by fractions of a degree, before night returns and the heat radiates back into space. The spacecraft continues its lonely vigil orbiting, while Mars orbits watching seasons turn with patience no human could sustain. Its instruments will eventually fail, batteries wearing out, or electronics succumbing to radiation damage, but for now, it functions. It observes, it sends back images and spectra and measurements that add detail to our understanding of this world that shares our sun, but little else. And perhaps that's the deepest lesson of Martian seasons, the way they demonstrate that time passes everywhere, that change is universal, even if the specifics vary. Earth marks time with life. with growing and dying and growing again, cycles that have repeated for billions of years and that make our seasons feel vital, necessary, full of purpose. Mars marks time with ice and dust, with thermodynamics and orbital mechanics, with processes that are no less real, but that feel empty, devoid of the meaning that life assigns to seasonal change. Yet the ice still advances, the dust still rises, the seasons still turn. Mars doesn't need life to have seasons, doesn't need observers to mark the passage of time. The universe counts its own rhythms in phenomena. We're only beginning to measure in changes that dwarf human time scales, but that follow patterns we can, with patience and careful study, begin to understand. But understanding cycles of ice and dust only takes us so far toward the question that haunts every Mars mission, the quiet wondering that persists beneath every measurement and photograph, the possibility that these cycles, these seasons of silence might not always have been so empty, that perhaps there were other seasons here, once warmer and wetter seasons that something living might have witnessed, might have responded to, might have survived through before the long decline into the frozen present began. Zhurong carries no life detection instruments in the traditional sense, no microscopes to search for cells, no DNA sequencers, no culture chambers where Martian microbes might grow if given the right nutrients and conditions. That's not an oversight. It's a reflection of how difficult the question of Martian life actually is, how complex the search becomes when you don't know what you're looking for. Life on Earth is diverse beyond cataloging millions of species filling every conceivable niche, but all of it shares fundamental characteristics. DNA or RNA for heredity proteins, for structure and catalysis, lipid membranes to define boundaries between self and environment. We know how to detect Earth life because we know what Earth life is made of, what chemicals indicate its presence, what structures betray its activity. But Martian life, if it exists or existed, might be built differently. It might use different genetic molecules, different membrane chemistry, different metabolic pathways. Searching for Earth-like biosignatures might miss something genuinely alien, something that lives or live by rules we haven't yet imagined. So, Zhurong takes a different approach. It characterizes the environment maps. The chemistry and geology identifies locations where life as we understand it could potentially have survived. The search for actual organisms, actual proof of biology that comes later, with more sophisticated missions, with sample returns that bring Martian material to Earth laboratories, where every possible test can be applied. But the rover's findings hint at possibilities at environments that might once have been habitable, even if we can't yet say whether they were inhabited. Those hydrated minerals detected in various rock samples, for instance minerals that formed in the presence of water, are exactly the kind of materials where biosignatures might be preserved if life ever existed nearby. On Earth, some of our oldest evidence for life comes from similar minerals, from rocks that formed in ancient oceans, and that contain chemical and structural anomalies best explained by biological activity. Stromatolites layered structures created by bacterial mats date back 3.5 billion years or more. Certain carbon isotope ratios in even older rocks suggest biological carbon fixation organisms taking CO2 from the atmosphere and incorporating it into organic molecules with a preference for the lighter carbon, 12 isotope over carbon 13. Mars had liquid water at the surface during the same epoch when Earth's first life appeared. The chemistry was similar, the basic ingredients present. If life arose on Earth during that window, why not on Mars? The question isn't whether Mars could have supported life. The geology answers that affirmatively. The question is whether the transition from chemistry to biology actually occurred, whether the improbable step from complex organic molecules to self-replicating systems happened twice in our solar system or only once. The answer matters profoundly for understanding how common life might be throughout the universe. If life arose independently on two planets in the same solar system, It suggests that the emergence of biology is relatively easy, that given liquid water and the right chemistry, life appears readily inevitably almost. This would imply that the universe is full of living worlds, that we're not alone in any meaningful sense, that biology is as fundamental and widespread as physics and chemistry. But if Mars is and always was lifeless, despite having conditions similar to early Earth, that suggests life's origin is harder, rarer, dependent on factors we don't yet understand. Maybe Earth got lucky. Maybe some additional ingredient was necessary, something Mars lacked. In that case, living worlds might be extraordinarily rare, separated by vast distances, islands of biology in an ocean of sterile chemistry. We don't know yet. The data we have is tantalizing, but inconclusive, suggestive, but not definitive. Jurong's chemical analyses show that Utopia planitia once had abundant liquid water, that the water persisted long enough to alter rock chemistry, that organic molecules from space should have accumulated in that water over millions of years. These are promising signs, but they're not proof of life, not even close. There's a common misconception that needs addressing here. Many people assume that finding water on Mars means finding life, that the presence of H2O automatically implies biology. This conflation appears in media coverage and casual conversation, sometimes even in how scientific discoveries are presented to the public. But water is necessary for life. As we know it, not sufficient for it. The moon has water ice at its poles. Comets are largely water ice. Europa and Enceladus moons of Jupiter and Saturn have subsurface oceans containing more water than all of Earth's oceans combined. Yet we don't assume these places are teeming with life. We acknowledge that water is just one requirement among many. Life needs water, yes, but also a stable environment where complex chemistry can occur over long periods. It needs energy sources, ways to drive reactions uphill against entropy. It needs organic molecules, the carbon-based compounds that form the scaffolding of terrestrial biochemistry. And it needs time, vast stretches of time measured in millions of years, for random chemistry to explore the space of possible molecules until it stumbles upon combinations that can replicate, that can evolve, that cross the threshold from merely complex to genuinely alive. Mars had water and time. The energy sources existed: sunlight at the surface, chemical gradients, and subsurface environments. Organic molecules fell from space, continuously delivered by meteorites and cometary dust. The stage was set. But did the play actually occur? Did chemistry on Mars ever become biology? Or did something prevent that transition, some missing ingredient or some threshold that was never quite crossed? One possibility involves the timescale of habitability. Mars's warm, wet period lasted perhaps 1 billion years, from about 4 billion years ago to 3 billion years ago, give or take a few 100 million years, in either direction. That sounds like plenty of time, and in human terms, it's unimaginably long. But it's only a third of Earth's history, only a third of the time life had to emerge and diversify here. On Earth, the earliest definitive evidence for life dates to about 3.5 billion years ago, roughly 500 million years after the planet cooled enough for liquid water to exist. That gives an upper bound on how quickly life can emerge, somewhere between a few million years and 500 million years. We can't pin it down more precisely than that. If Mars had 1 billion years of habitable conditions, that should have been sufficient. But maybe the window was narrower than we think. Maybe habitable conditions appeared and disappeared multiple times, giving chemistry false starts, periods where interesting molecules formed only to be destroyed when conditions deteriorated again. Or maybe life did arise on Mars, and we simply haven't found evidence yet. Mars is large, about half Earth's diameter, with a surface area equal to all of Earth's land area combined. Jurong has explored a tiny fraction of one region. The rover has traveled about 2 kilometers total, sampling perhaps a few dozen locations. Finding evidence of ancient life, if it was rare and localized, would be like finding a specific grain of sand on a beach by wandering around randomly for a few minutes. The odds aren't good unless life was abundant and widespread. This is why sample return missions are so crucial. Rather than relying on in situ analysis with limited instruments, scientists want to bring Martian rocks to Earth, where they can be examined with techniques that would be impossible to deploy on Mars. Electron microscopy to search for fossilized cellular structures, mass spectrometry sensitive enough to detect single molecules, isotope analysis that can distinguish biological carbon from abiotic carbon with high confidence. These tools exist in Earth laboratories, but they require infrastructure and power and expertise that can't be packed into a rover or lander. The Chinese space program has outlined plans for such a sample return mission, tentatively scheduled for the late 2020s or early 2030s, exact timeline, depending on technological readiness and budget considerations. NASA and ESA are pursuing similar missions, recognizing that this is the logical next step in Mars exploration. Bring samples home, let hundreds of laboratories analyze them, using thousands of different techniques, and see what emerges from that intensive scrutiny. But there's another place to look for Martian life, one that doesn't require waiting for sample returns or relying on lucky rover traverses. If life exists on Mars now, in the present, rather than the ancient past, it's almost certainly underground in aquifers or cavities, where liquid water might persist despite the frozen surface conditions. And if such life exists, we might already have samples of it here, on Earth, delivered by natural processes over billions of years. Mars and Earth exchange material constantly have been doing so since both planets formed. Large asteroid impacts on Mars eject rocks into space with enough velocity to escape Martian gravity. Those rocks orbit the Sun for thousands or millions of years before some percentage of them eventually intersect Earth's orbit and fall to our surface as meteorites. We've recovered thousands of Martian meteorites identified by their chemical composition and trapped atmospheric gases that match Mars's distinctive atmosphere. These rocks provide windows into Martian geology without requiring space missions. Could they also carry evidence of Martian life? In theory, yes. If subsurface life exists on Mars, if some of that life was present in rocks that got ejected into space, and if the organisms or their remains survived the shock of ejection, the radiation exposure during spaceflight, and the heat of atmospheric entry, then Martian life might have reached Earth, naturally might be sitting in museum collections, or still undiscovered in Antarctic ice fields where most meteorites are found. This possibility drives intensive study of Martian meteorites, careful searching for anything that might indicate biological origin. So far, nothing conclusive has emerged. There was excitement in 1996 when a team announced possible microfossils in a Martian meteorite called ALH 84001, tiny structures that resembled bacterial cells. But subsequent analysis showed that the structures were far smaller than any known cells that they could form through non-biological processes, that the evidence was ambiguous at best. The controversy over ALH 84001 illustrates how difficult the search for life beyond Earth really is. Finding something unusual isn't enough. Finding something that resembles life isn't enough. The evidence needs to be unambiguous, needs to rule out all plausible non-biological explanations, needs to meet standards of proof that are necessarily high, because the claim is so extraordinary. Carl Sagan famously said that extraordinary claims require extraordinary evidence, and claiming that we've found extraterrestrial life, even fossil life, even life from a neighboring planet, is about as extraordinary as claims get. The burden of proof is heavy, appropriately so, and scientists working on Mars missions understand this approach. Their data, with appropriate skepticism, avoid making claims that can't be firmly supported. But the search continues because the question matters. Not just scientifically, though, the scientific importance is obvious, but philosophically, existentially, as a question about our place in the universe. Are we alone? Is Earth's biosphere unique, or is life common, perhaps even inevitable given the right conditions? The answer changes how we think about ourselves, about the value and fragility of life, about whether the universe is fundamentally friendly or hostile to biology. Some scientists argue that we might be asking the wrong question. Instead of, did life ever exist on Mars? Perhaps we should ask, did Mars and Earth share a common biology? In the solar system's violent early history, when giant impacts were common, material was exchanged not just from Mars to Earth, but also from Earth to Mars. If life arose on Earth, first microbes could have been transported to Mars via impact, ejecta, seeding Mars with Earth life. In that case, any life found on Mars might be our distant relatives' descendants of terrestrial organisms rather than independently originated biology. This possibility makes the search more complex but no less important. Finding that Mars had life would still be profound, even if that life was related to Earth life. It would prove that life can survive interplanetary transfer, that it can adapt to dramatically different environments, that panspermia, the spreading of life between worlds, is a real phenomenon rather than science fiction speculation. There's also the question of extinction. If life did arise on Mars, whether independently or via transfer from Earth, why isn't it abundant and obvious now? The most likely answer is that Mars's habitability declined faster than life could adapt. As the atmosphere thinned, as water vanished from the surface, as radiation intensified, any surface life would have faced increasingly harsh conditions until finally the environment became completely intolerable. But extinction isn't always total. On Earth, life persists in extraordinary environments, in boiling hot springs and frozen Antarctic valleys, in acid mine drainage and salt-saturated lakes, miles underground in rock fractures, and at the bottom of oceans where no sunlight reaches. Extremophiles push the boundaries of what we thought possible for biology surviving and even thriving in conditions that would sterilize normal environments. If Martian life ever existed, might some hardy extremophiles persist in subsurface refuges? Might there be Martian microbes alive today clinging to existence in aquifers, warmed by geothermal heat and brine pockets that remain liquid despite surface temperatures far below freezing in cavities, where chemical energy from rock-water reactions provides the power for minimal metabolism? These aren't idle speculations. Similar environments exist on Earth and support vibrant microbial ecosystems. The deep subsurface biosphere life living in fractured rocks kilometers below the surface may contain as much biomass as all the life in Earth's oceans. These organisms survive on chemical energy oxidizing minerals, or reducing dissolved compounds living in darkness on time scales measured in centuries between cell divisions. Mars could harbor similar deep life, unreachable by surface rovers, undetectable by orbital instruments, persisting in isolation from the surface for billions of years. Finding such life would require deep drilling, penetrating through permafrost and impermeable layers to reach aquifers that might exist at depths of hundreds of meters or more. No current Mars mission has that capability, but future missions might, especially human missions, with heavy drilling equipment and the ability to explore systematically, rather than relying on robotic systems with limited flexibility. Until then, we're left with hints and possibilities, with environments that could have supported life with chemistry that suggests but doesn't prove biological activity. Jurong's data adds to this growing body of circumstantial evidence showing that Utopia Planitia had everything life needs, that the environment persisted long enough that if life ever existed anywhere on Mars, it could have existed there. But potential and actuality are different things. A habitable environment doesn't guarantee inhabitants. An empty house is still a house, whether anyone lives there or not. Mars might be the empty house of the solar system, perfectly suitable for life, but never occupied, standing vacant despite having all the necessary amenities. Or it might be occupied still by tenants we haven't yet met, living in the basement, while we examine the abandoned upper floors, making judgments about emptiness based on incomplete exploration. The question remains open, and perhaps that openness is itself meaningful, a reminder that despite all our instruments and rovers and orbital surveys, Mars still holds mysteries, still guards secrets that we're only beginning to approach with the right questions and the right tools to find answers that satisfy both scientific rigor and human curiosity about whether we're alone in this corner of the universe, or whether life in some form has found multiple footholds among the worlds that share our sun. In November 2022, while Zhurong had already entered hibernation mode on the Martian surface, Chinese officials announced something that shifted the conversation from scientific discovery to human ambition. They outlined plans still preliminary, but growing more concrete to land Chinese astronauts on Mars sometime in the 2030s or early 2040s. Not robots this time, not rovers or orbiters sending data back across millions of miles, but humans in pressure suits standing on Martian soil, looking up at a sky that's never seen clouds like Earth's breathing recycled air, living in habitats that would be home for years before a return launch becomes possible. The announcement wasn't unexpected. China's space program has followed a methodical path. Satellites, then crewed Earth orbit, then a space station, then lunar orbiters and landers, then Mars orbiters and rovers. Each step builds capability tests. Technology trains personnel. Mars is the logical next destination for a program that's demonstrated both patience and ambition, that operates on timelines measured in decades rather than election cycles. But landing humans on Mars isn't just a next step. It's a discontinuity, a shift from observation to participation, from studying a world to becoming part of it, however temporarily. And every discovery that Tianwen-1 and Zhurong make feeds into planning for that eventual human presence, answering questions about where to land, what resources exist, what challenges await. Consider what we've discussed in this journey so far. Subsurface ice within meters of the surface, chemistry that includes both useful materials and toxic compounds requiring careful management, weather patterns that include dust storms and temperature swings that would challenge any equipment or habitat, seasons that last nearly twice as long as Earth's. And underlying all of it, the question of whether life might exist in hidden refuges, which introduces both scientific opportunity and planetary protection concerns. Every one of these factors shapes human mission planning. The ice, for instance, transforms mission architecture. Without accessible water, a Mars mission would need to bring everything from Earth water, for drinking oxygen, for breathing hydrogen, for rocket fuel. The masses involved would be enormous, the costs prohibitive. But if water exists at the landing site, if it can be extracted and purified, suddenly the mission becomes feasible with current or near-future technology. Zhurong's ground-penetrating radar data doesn't just tell us ice exists. It maps where it's most accessible, where drilling would need to penetrate only a few meters rather than tens of meters, where the ice appears to be relatively pure rather than mixed with high concentrations of dust. This information directly informs landing site selection for future missions. A location with easy access to ice moves up the priority list, assuming it also offers other advantages like relatively flat terrain for landing interesting geology, for scientific study, and good communication angles with Earth. The chemical findings matter too, particularly those perchlorates we discussed earlier. Knowing they're present means mission planners must design water purification systems, soil remediation for agriculture, and dust management protocols to prevent toxic compounds from entering habitats. These aren't insurmountable challenges, but they're real constraints that affect everything from life support systems to the types of materials used in pressure suits and airlocks. The weather data influences habitat design, power systems, and operational planning. Those dramatic temperature swings from -20 degrees to -100 degrees Celsius require heating systems that can operate reliably across that range. The dust storms affect solar panel efficiency, suggesting that missions should include backup power sources, perhaps nuclear reactors like the radioisotope thermal generators that power some current rovers. And the seasonal patterns, those long Martian years where winter extends for 11 Earth months, create psychological challenges as much as physical ones. Humans evolve for Earth seasons, for cycles of growth and dormancy that repeat every 12 months. Adapting to a 24-month cycle where summer and winter each last nearly a full Earth year would require psychological preparation and support. Astronauts would need to maintain motivation and mental health through periods that feel interminable, where the environment outside offers no variation, no natural markers of passing time beyond the slow tracking of the sun through its seasonal arc. But there's a deeper question underlying all the technical planning, one that's easy to overlook amid discussions of landing sites and resource extraction. Why should humans go to Mars at all? What's gained by sending people rather than increasingly sophisticated robots? This question generates fierce debate among scientists, engineers, and policymakers. Some argue that robots are cheaper, safer, more expendable, and can be designed for specific tasks without the complications of life support. Others insist that human flexibility, intuition, and ability to respond to unexpected situations make crewed missions worthwhile, despite their greater cost and risk. The scientific case for human missions rests partly on efficiency. A human geologist can accomplish in hours what takes a rover weeks or months. They can make intuitive judgments about where to look, what to sample, how to interpret field relationships between different rock types. They can cover distances that rovers crawl across over years. And they can perform complex sample collection and documentation that would be nearly impossible to automate reliably. But there's also an inspirational argument harder to quantify, but perhaps equally important. Human spaceflight captures public imagination in ways that robotic missions rarely do. The Apollo moon landings inspired generations of scientists and engineers, created a shared cultural moment that transcended national boundaries. A human landing on Mars would be similar, perhaps more so, given that Mars is farther harder to reach a genuine frontier rather than a nearby destination. China's space program seems to embrace both rationales, pursuing robotic exploration, while preparing for eventual human missions, treating them as complementary rather than competing approaches. The data from Tianwen-1 and Zhurong directly enables future crewed missions by characterizing the environment, identifying resources, mapping hazards. And when humans eventually arrive, they will build on this robotic foundation, using knowledge accumulated by machines to make informed decisions about where to go and what to study. There's also a geopolitical dimension that can't be ignored. Space exploration, particularly human spaceflight, carries symbolic weight. It demonstrates technological capability, long-term planning ability, and national ambition. When China successfully landed Zhurong on Mars on the first attempt, something no other nation had achieved, it announced that China had arrived as a major spacefaring power. A crewed Mars landing would be an even stronger statement, placing China alongside or ahead of the United States in humanity's expansion beyond Earth. This competition might seem problematic, reminiscent of Cold War space races driven more by nationalism than scientific curiosity. But competition also drives, progress creates urgency and funding that purely scientific motivations might not generate. The Apollo program happened because the United States wanted to demonstrate superiority over the Soviet Union. The science, however valuable, was secondary to the geopolitical goals. But we got to the moon, and we learned things we couldn't have learned otherwise, and the technology developed for Apollo had spillover effects that benefited fields far beyond spaceflight. A new space race to Mars, if that's what emerges, might similarly accelerate development of technologies with broad applications. Better life support systems, improved materials, science more efficient energy generation, and storage advanced robotics and artificial intelligence enhanced manufacturing techniques. The innovations required to keep humans alive on Mars for years would necessarily push multiple fields forward, and those advances would find uses on Earth as well. But let's be clear about the challenges. Mars is not a hospitable place. The surface receives radiation doses that would cause serious health problems over months or years of exposure. The partial gravity, about 38% of Earth's, might have long-term effects on bone density, muscle mass, and cardiovascular function that we don't fully understand yet. The psychological stress of isolation, of living in confined spaces with the same small group of people, of being unable to walk outside without a pressure suit, of knowing that rescue is impossible if something goes catastrophically wrong, these are factors that could break missions even if the technology performs flawlessly. Antarctic research stations provide some analogy. People winter over in Antarctica, living for months in isolation, dealing with extreme cold and darkness, maintaining psychological health through structured routines and careful crew selection. But Antarctica has an escape option, however difficult. An emergency evacuation is possible even in winter, even if it's dangerous. Mars offers no such option. A medical emergency, a critical equipment failure, a psychological breakdown, these would have to be managed with whatever resources exist on Mars. Help from Earth is 11 minutes away by radio signal, months away by actual travel time. Would you go, knowing these risks? If offered a seat on the first crewed Mars mission, knowing you'd spend 6 months in transit a year, or more on the surface and another 6 months returning, would you accept? It's easy to say yes from the comfort of Earth, harder when you're actually facing the reality of confinement, radiation exposure, and the genuine possibility of death. Yet history suggests there will be volunteers, plenty of them. Humans have always had a subset of individuals willing to risk everything to explore, to go where others haven't to be first. The Chinese Space Agency will select carefully, looking for not just technical competence, but psychological resilience, team, compatibility, ability to function under stress. The crew will train for years practicing in simulators and analog environments on Earth, learning to work together to trust each other completely because their lives will depend on that trust. And they'll rely on data from missions like Tianwen-1 and Zhurong, studying the findings, memorizing maps, understanding the seasonal patterns and weather risks. The rover tracks that Zhurong left in Martian soil might someday be visited by humans who'll stand where the rover stood, seeing with their own eyes the landscape that we've only viewed through transmitted images. What will that first moment feel like when a human first steps onto Martian soil? Not the rehearsed broadcast moment that will be documented and analyzed and remembered, but the personal, private experience of that individual, the subjective reality of standing on another world, of looking around at a horizon that's never known, footprints of breathing artificial air, while surrounded by an atmosphere too thin to breathe, of knowing that everyone you've ever known except your crewmates is on another planet millions of miles away. The moon landing gave us one famous quote: "That's one small step for man, one giant leap for mankind." Mars will generate its own historic words, though. Whether they'll be in English or Mandarin or some other language remains to be seen. The words themselves matter less than what they represent. Another threshold crossed another boundary, expanded another world, where humanity has established presence, however tenuous and temporary that presence might initially be. But establishing permanent presence, creating a self-sustaining Mars base or settlement, that's generations away at minimum. The first missions will be visits, brief encampments, not settlements. The distinction matters. Visitors leave taking their waste and leaving only footprints and perhaps some equipment. Settlers stay, which means establishing closed-loop life support, growing food, manufacturing spare parts, building infrastructure that doesn't depend on constant resupply from Earth. The ecological concerns this raises are profound. Mars is currently pristine, at least by one definition of pristine. It's untouched by Earth life, by industrial contamination, by the changes that human presence inevitably brings. Should we preserve Mars in its current state? Or is human expansion to other worlds not just acceptable, but morally imperative, ensuring that life has multiple homes, that a catastrophe on one world doesn't extinguish consciousness in the universe? These aren't questions with clear answers. They involve values, philosophies, competing visions of humanity's role in the cosmos. Some argue that Mars belongs to itself, that we have no right to contaminate or terraform it, that any life it might harbor deserves protection from invasive Earth biology. Others argue that lifeless worlds have no interests, no rights, that humans have both the ability and the right to spread to other planets to ensure our species' long-term survival by becoming multi-planetary. China's space policy documents don't explicitly address these philosophical questions, focusing instead on scientific exploration and technological capability demonstration. But implicit in planning for human Mars missions is an assumption that such missions are legitimate, that exploring and potentially utilizing Mars resources falls within acceptable human activity. Whether this implicitly accepts eventual settlement or just endorses temporary human presence remains ambiguous, probably deliberately so. The discoveries from Tianwen-1 and Zhurong don't resolve these philosophical debates, but they provide crucial information that makes the debates concrete rather than abstract. We're not arguing about a hypothetical Mars anymore. We're discussing a real place with specific characteristics, with ice and mapped locations, with chemistry we've analyzed, with weather patterns we've documented. The conversation shifts from what might Mars be like to, given what Mars is actually like, what should we do? And perhaps that shift from speculation to informed decision-making is part of what makes the Tianwen mission significant beyond its scientific findings. It's moving Mars from the realm of imagination into the realm of planning, from a dot of light in the night sky, into a place with topography and resources and challenges, a destination rather than a dream. Whether humans should go there, whether we'll establish permanent presence, whether Mars will become a second home or remain an object of study, these questions remain open. But they're no longer purely hypothetical. They're practical considerations requiring practical answers, decisions that will be made not by philosophers or science fiction authors, but by mission planners and politicians, by engineers calculating delta VC budgets, and by medical professionals assessing radiation risks. The data streams down from orbit from the rover sleeping in Martian winter, and it feeds into spreadsheets and simulations, into risk assessments and mission timelines, into the slow accumulation of knowledge that will someday perhaps, soon perhaps, in a decade or two, result in human bootprints beside Zhurong's wheel tracks, in voices speaking across the Martian plain, and the first tentative steps toward answering not just whether humans can reach Mars, but whether we can stay, whether we can build something lasting, whether this red world that lost its oceans billions of years ago might someday hear the sound of flowing water, again of machinery humming, of people living lives that are genuinely Martian, rather than merely Earth lives temporarily transplanted. But before those futures arrive, before plans crystallize into missions and missions into reality, there's a quieter moment to acknowledge a recognition that everything discussed here, all the discoveries and implications and possibilities emerge from a rover and orbiter that are at their core, simply machines doing what machines do, collecting data in environments hostile to their function, persisting through cold and dust and radiation, sending signals home across distances that make the mind falter, contributing to human knowledge without asking why or whether their efforts matter, functioning until they can't, leaving behind silence and the slow accumulation of dust over mechanisms that briefly brought motion and purpose to a landscape that had known neither for billions of years. On May 20th, 2022, after nearly a full Martian year of exploration, Zhurong sent its last transmission before entering hibernation mode. The message was simple: routine telemetry. Data power levels dropping as Martian winter approached and dust accumulated on solar panels. Mission controllers expected the rover to wake when spring arrived and sunlight strengthened just as it had awakened from previous dormant periods during dust storms. But spring came, and summer, and Zhurong remained silent. Engineers sent wake-up commands, listened for responses that never arrived. By August 2022, mission managers quietly acknowledged what the silence suggested: Zhurong had likely ended its operational life, joining a growing collection of human artifacts scattered across the Martian surface machines that explored until they couldn't, then became part of the landscape they came to study. There's a particular loneliness in this ending, something that transcends the mere cessation of mechanical function. Zhurong sits there still, wheels locked in place, solar panels coated with the dust that finally overwhelmed its ability to generate power. Its cameras still point at the same view they captured in that final transmission, unchanging, because there's no wind strong enough to turn the mast, no processes to alter its configuration. The rover is frozen not in ice, but in time, a monument to the moment its batteries depleted below the threshold needed for operation. Somewhere in Utopia, Planitia, in a position marked precisely by coordinates, but that would be nearly impossible to locate without those coordinates given the uniformity of the surrounding terrain. Zhurong waits. Not in any conscious sense machines don't wait or hope or dream, but it occupies space, reflects light, casts a shadow that moves with the sun, and in that physical persistence, there's a kind of presence that feels meaningful, even though meaning is something we impose rather than something inherent. Think about what it accomplished in its operational lifetime. Nearly 2 kilometers of traverse each meter, representing cautious navigation around obstacles, careful selection of paths that avoided hazards, balancing scientific objectives with the imperative to survive long enough to achieve them. Dozens of rock and soil samples analyzed each one, adding data points to our understanding of Martian chemistry and geology. Hundreds of weather measurements mapping how temperature and pressure and wind vary through the Martian day and across seasons. Thousands of images, some spectacular and worthy of artistic appreciation, others mundane and purely functional, all of them pieces of a larger portrait of a world we're only beginning to understand. The ground-penetrating radar data, alone those echoes from subsurface layers that revealed ancient water and buried ice, would justify the mission. But there's more: the accumulated weight of all the findings taken together, the way each measurement confirms or refines or occasionally contradicts what we thought we knew, pushing our understanding forward in increments that seem small individually, but that add up over time to genuine progress. And Tianwen-1 continues. The orbiter still circles Mars every 7 hours, still maps the surface in multiple wavelengths, still measures atmospheric properties and magnetic fields, still serves as a relay for any future Chinese missions that might arrive. Its fuel will eventually run low, or some component will fail from radiation damage or simple wear, and it too will fall silent. But for now, it persists, it functions, it sends data home across the void. That data arrives at Chinese ground stations, massive dishes that track the signal as it sweeps across the sky, extracting information from radio waves that traveled millions of miles and still carry enough coherence to be decoded into images and measurements. Scientists analyze the data, publish papers present at conferences, gradually building the body of knowledge that future missions will draw upon. The process is slow, methodical, unglamorous. But this is how science works at its best, through patient accumulation of evidence, through careful analysis that admits uncertainty, through peer review and replication, and the gradual convergence toward truth, or at least toward models that predict observations better than previous models did. What have we learned really from China's surprising findings on Mars? Not surprising in the sense of being completely unexpected. Most of the discoveries confirmed what orbital observations and previous missions had suggested, but surprising in their detail, in the clarity with which they demonstrate that Mars was once a very different world that the transformation from ocean planet to frozen desert wasn't instantaneous, but unfolded over hundreds of millions of years, that the ingredients for life were present even if we can't yet say whether life itself arose. We've learned that Mars is more dynamic than it appears. The dust devils dancing across plains, the seasonal breathing of the atmosphere, the slow migration of ice between hemispheres. These are ongoing processes, evidence that Mars isn't geologically dead, even if it's less active than Earth. The planet still changes, still responds to solar heating, and orbital mechanics still has weather and seasons and cycles that play out over years and decades and millennia. We've learned that water exists in forms and locations that make it accessible to future missions, that the ancient dream of humans living on Mars isn't just science fiction, but might actually be achievable given sufficient investment and technological development. The challenges are enormous, the risks real, but the resources exist. The destination isn't completely hostile. There's reason to think we could survive there if we're clever and careful and perhaps a bit lucky. We've learned that Mars had time, had conditions, had chemistry that could have supported life during its warm, wet period billions of years ago. We still don't know if life arose, but we've narrowed the question, focused the search, identified the kinds of locations where evidence might exist if we look carefully enough. The question has shifted from, could Mars have had life, to, how do we find out if it did? And perhaps most profoundly, we've learned that Mars isn't as alien as we imagined. It's different from Earth, certainly colder and drier and thinner aired, but it's not incomprehensible. The same physical laws apply, the same chemistry, operates the same types of geological processes, shaped its surface, even if the details differ. Mars is strange but recognizable, foreign but not entirely other. It's a place we can understand, can study, can perhaps someday inhabit. But beyond the specific findings, beyond the data and measurements and scientific papers, there's something else worth acknowledging. The Tianwen mission represents a shift in how humanity explores space, a transition from American and Soviet dominance to a more multipolar reality, where multiple nations contribute to our collective knowledge of the solar system. China's success on Mars, achieving on the first attempt, what took other nations multiple missions to accomplish, demonstrates that space exploration is no longer the exclusive domain of a few countries, that new players are emerging, with both the technical capability and the sustained commitment needed for ambitious missions. This democratization of space exploration, if we can call it that, benefits everyone. More missions mean more data, more perspectives, more chances to find unexpected things. Different approaches and priorities lead to different landing sites and instrument selections, broadening the scope of exploration beyond what any single space agency might pursue. And the implicit competition, the desire to demonstrate capability and achieve firsts, creates urgency that might otherwise be lacking. Some worry about a new space race, about nationalistic competition, leading to unnecessary risks or wasteful duplication of effort. But cooperation and competition aren't mutually exclusive. Chinese scientists collaborate with international colleagues, share data through established channels, participate in the same conferences and peer review processes that define modern science. The missions might be national in funding and organization, but the knowledge they generate belongs to humanity as a whole. And sitting at the center of China's contribution is Zhurong, silent now, but permanent, a machine that became momentarily famous when it landed successfully, then faded from public attention as it went about its work, and now exists in a strange liminal state between forgotten and remembered, between finished and somehow still present. Do you think about the rovers sometimes? Not just Mars rovers, but all the spacecraft we've sent to other worlds, the machines that carry our curiosity to places we can't yet go ourselves. They're not alive, not conscious, not aware of their achievements or their endings, but we project onto them, assign them personalities, mourn them when they fail, celebrate their accomplishments as if they were personal triumphs, rather than the product of thousands of people working for years to make a mission succeed. Perhaps that projection is necessary. Perhaps it's how we make sense of exploration by proxy, how we maintain emotional connection to missions that unfold over years and decades in environments we can barely imagine. The rovers become avatars representing human curiosity and persistence, embodying our desire to understand worlds beyond our own. Zhurong did that. It represented not just Chinese technological achievement, but human achievement more broadly, the peculiar drive we have to look beyond horizons to ask, what's there to not be satisfied with ignorance when knowledge might be obtainable? That drive has led us to every corner of Earth, to the ocean depths and mountain peaks and polar wastes. Now, it leads us into space to the moon and Mars, and eventually beyond, following curiosity wherever it leads. The rover sleeps in Martian winter, and winter extends for months, and when summer comes again, the solar panels might clear enough for power to return. For systems to reboot for one more transmission to cross the void, and tell us that against expectations, against the odds, Zhurong has awakened. Or winter might give way to spring, and spring to summer, and the silence might continue permanent, now the end of the mission official rather than merely probable. Either way, the contribution persists. The data exists in archives available to any researcher who wants to analyze it. The maps have been made showing ice locations and mineral distributions and weather patterns. The knowledge has been integrated into our understanding of Mars, has informed mission planning for future exploration, has answered some questions and raised new ones that the next generation of missions will investigate. And somewhere in China, in laboratories and universities, in space agency facilities, engineers and scientists are already working on those next missions. Learning from Tianwen-1 and Zhurong, designing improved instruments and more capable rovers, planning landing sites and scientific objectives, preparing to continue the exploration that Zhurong began. The story doesn't end. It never ends, really. Each mission is a chapter. Each discovery opens new questions. Each spacecraft that falls silent is eventually succeeded by new arrivals that build on what came before. Mars will host more rovers, more orbiters, eventually humans walking across the same plains where Zhurong drove. Those humans will benefit from what Zhurong learned, will use the maps it helped create, will draw water from ice deposits that Zhurong's radar first detected. In that sense, the rover's legacy extends beyond its operational lifetime, becomes part of the foundation on which future exploration is built. And when humans finally do arrive, when they stand in Utopia, Planitia, and look around at a landscape that's no longer just images and data, but actual terrain they can touch and walk across, perhaps some of them will seek out Zhurong's location, will stand beside the silent rover and acknowledge the role it played in making their presence possible. Or perhaps they won't. Perhaps by then, there will be so many spacecraft scattered across Mars that individual missions are taken for granted, that Zhurong is just one name in a long list, historical, but not particularly special. That would be fine too in its way. It would mean we'd succeeded, that Mars exploration had become routine enough, that early missions were simply the beginning of a story that continued far beyond them. But in this moment, before that future arrives, Zhurong deserves recognition for what it achieved, for the knowledge it gathered, for the questions it answered, and the new questions it raised. Mars is less mysterious because of this mission, more real, more accessible, closer to being a place we might someday call home, rather than just a distant destination we study from afar. The red planet spins in its orbit, carrying Zhurong and Tianwen-1 with it, along with all the other spacecraft that have reached Mars over the decades. Some still function, some don't, but all are testament to human curiosity, to our refusal to be bound to a single world, to our insistence on exploring and understanding, and eventually perhaps expanding beyond the cradle that gave us birth. Mars doesn't need us. It existed for billions of years before humans evolved, will continue for billions more after we're gone if we fail to survive as a species. But We need Mars, or at least we need what Mars represents. Possibility challenge, a frontier that demands our best efforts and rewards them with knowledge. A reminder that the universe is vast and mysterious and full of places we haven't yet explored. Tonight, Mars is visible in the evening sky, a rust-red point of light that doesn't twinkle the way stars do because it's close enough that its light isn't distorted by our atmosphere as much. Look for it if the sky is clear. Remember that it's not just a light, but a world, a place with mountains and canyons and polar ice caps with dust devils and seasons and buried layers of ice with a history that parallels Earth's, but took a different path, with a future that might include our descendants living in habitats built with Martian materials, breathing air generated from Martian resources, existing as a multi-planetary species, no longer confined to one world. Zhurong helped bring that future slightly closer, not through any single dramatic discovery, but through the patient accumulation of knowledge, the methodical characterization of the environment, the demonstration that Mars is comprehensible and approachable, challenging, but not impossible. And now the rover rests its work complete, or at least suspended, while the planet it came to study continues its ancient rotation wheels through its orbit, experiences. Seasons that will repeat long after every human alive today has died, after our civilization has either expanded to the stars or vanished from existence after everything we think. Important has been forgotten by the universe that cares nothing for our concerns, but that graciously through physical law and chemical possibility allows us to exist, to wonder, to explore, to briefly illuminate tiny corners of the darkness with our curiosity and our machines and our stubborn insistence that knowledge is worth pursuing for its own sake. Sleep well, Zhurong. Your journey has ended, but the journey you helped begin will continue as long as humans exist, to look up at the night sky and wonder what's there, as long as we refuse to accept that Earth is enough, that one world can contain all our dreams and ambitions and questions. Dream gently if machines can dream. And know if machines can know anything, that your contribution matters, that you changed how we see Mars, that you're part of a story larger than any single mission, larger than any nation's achievement, a story of human exploration and discovery that started in caves and forests and now reaches across space to worlds that orbit the same star. We do worlds that are no longer just points of light, but destinations, places we've touched with our machines and will someday touch with our hands. Thank you for joining me on this quiet journey across space and time, through data and discovery, through the patient work of machines millions of miles away, doing what we built them to do, exploring, measuring, sending back whispers of knowledge from a world that once might have bloomed with life, but that sleeps now in silence, waiting for questions. We're only beginning to learn how to ask. I hope these stories of Mars, of ice and dust and ancient waters, have given you something to carry into your own sleep, some sense of wonder at how far we've come and how much farther we might go, some appreciation for the dedicated people who make these missions possible, and for the machines that execute their designs with patience beyond human capability. Until we meet again in another quiet night, in another story told softly, I wish you rest and peace and dreams of horizons yet unexplored. May your own journey, wherever it leads, be filled with the same curiosity that drives us to other worlds, the same persistence that keeps rovers rolling across alien landscapes, the same hope that tomorrow might answer questions we couldn't even formulate today. Good night, friend. The stars are waiting, and so are the stories we'll tell about them.